It's a great pleasure to introduce today's speaker. Before I introduce, actually, I'd like to ask everyone, how many of you use digital cameras? Maybe I should ask the other question. How many of you not use or have not used digital cameras? I'd like to ask one more question, but you don't have to answer. How many of you have used the camera pill for the camera pill? The pill in for looking at digestive tracts. So this is kind of for looking intestinal or health-related problems. The person behind all this technology is Professor Eric Fossum, our today distinguished colloquium speaker. Professor Fossum is a distinguished professor at Dartmouth University. He has a very interesting career. He started his career as assistant associate professor in Columbia University in the 80s. And right around the time in the 1990s when digital cameras, or sort of the end of the era of CCD cameras, he took a position at JPL, Jet Proportional Lab at Caltech, and started working on what we know today as the digital camera, or active pixel sensors. And he was the leading force to kind of develop and push this technology on the research side. And about mid-1990s, he started a company to commercialize this technology. So Photobit was the first digital or first company that he co-founded that commercialized digital cameras, and it was in every single devices. It's probably safe to say the first camera that was in the cell phone, his company was closely involved in this technology. So he has tremendous contributions, scientific contributions in moving or developing the CMOS technology, and probably credit for the end of the CCD era in some sense too. He's received numerous awards for his work, and I want to just single out one particular award that not many people probably know in engineering, and this is the Queen Elizabeth Award. It's a relatively new award. It's a 6-year award. It's given every 2 years worldwide for the best engineer. It's equivalent to the Nobel Prize in engineering. And it's given every 2 years, so he's the third recipient of this award. He received it this year by her son, Charles, Prince Charles, in the Buckingham Palace. So without delaying any further, actually one more thing. We have a special present for coming to our colloquium. Thank you so much.
Oh, thank you very much.
Please, everybody, join me in welcoming.
So this is my first time ever at the University of Illinois. So thank you all for the good weather. And no, this is an amazing campus. It's so huge compared to our small school out in the woods of New Hampshire, which we have about 100 engineering students across all disciplines every year. So that's like this part of the auditorium right here. It's always fun to come to a big school. So thank you very much, Professor Grue, for inviting me, and on behalf of the whole ECE department. So I am going to tell you a little bit about image sensors. I always say that if you go to a music concert, especially with one of the older bands, you can imagine that the band, let's say it was the Rolling Stones or something, they've played this like the same music for what, 40, 50 years? And that's what the fans really want to come and hear about. Probably in the back of their heads are thinking, we really want to play our new music. So I kind of feel the same way. I want to tell you about some of the new stuff that I'm doing, but also I think it's good to tell you about the background on CMOS image sensor technology development. So the new stuff is the Quanta Image Sensor, but before I really dive into that, I'm going to play some old music for you. Not really, but I'll talk about this stuff. CMOS image sensors, and of course this is the technology that you all have in your pocket these days. So every year there are billions of cameras made with CMOS image sensor technology in it. used everywhere. It always amazes me wherever I go in the world. There's always people taking pictures, a lot of selfies. If you look at the number of uploaded pictures per day, I found this data. I don't know if I can, it's not, you can't really see this, but anyway, at least out to 2015, there's really a strong growth. In 2015, there was over 3 billion pictures uploaded every day to the internet. 3 billion pictures in one day. Just think about that. It's mind-blowing. And being a good engineer, I decided to plot that on a log scale down below here. And you see that the doubling rate actually works out to be doubling about twice every year. So if this trend has continued, I don't know if it has, we are up somewhere around over 10 billion photos per day being uploaded to the internet. So I hope you've all done your duty today and uploaded a picture. There are all kinds of digital cameras. Of course, we're all familiar, okay, this pointer is not going to work too well. We're all pretty familiar with the cell phone camera, but there are digital still cameras, there are web cameras. We're talking about the pill camera, that's in the middle. That's actually a camera that you swallow. It takes pictures of your intestines. We actually did work on this in the very early days, enabled the very first one of these pill cameras. It's a disposable camera, by the way, in case you're wondering. Oh, thank you. And then these are dental X-ray sensor cameras. If you've gone to the dentist and the dentist is taking pictures of your teeth, it also uses a CMOS image sensor technology, and drones and body cams and that sort of thing. So all over the place. So let me tell you a little bit, just brief history of some of these things. So probably the very earliest solid state image sensors were built from MOS. I call it 0th generation because they didn't actually go into any real products or anything at the time, but it was some very early work that's worth acknowledging by Peter Nobel in the UK and Gene Weckler in the US at Redicon, but they actually built some small arrays of pixels up to 64 by 64, for example. And Peter also invented this first active pixel sensor device back in 1966. But what really took off was the charge-coupled device. So the charge-coupled device was invented in Bell Labs in 1969, and then the CCD image sensor was also invented at Bell Labs in 1970, and then perfected in mass production in Japan, especially in the 80s. And it became the mainstay of digital cameras and camcorders in the 80s and the 90s, and many of you weren't here then, but they were big cameras. We'll see a picture of that in a moment. So the way CCD worked, how many of you, by the way, know about semiconductor devices? Yeah, about half, okay. I'm not going to dwell too long on semiconductor devices, but obviously it's a big part of this discussion. So this CCD works by essentially a bunch of MOS capacitors that are electrodes on the surface of the semiconductor, and we apply a sequence of voltages to these electrodes. And then the electrons underneath in the semiconductor are dragged along as we pulse the voltage from electrode to electrode. But there's an insulating layer in between here, so the electrons can't actually go up into the electrode. So you can basically just keep shifting this charge for a long period of time, like all the way down this shift register. And in fact, it could go down this shift register and then down this fast shift register out to the corner of a chip where there's an amplifier. And every one of these cells actually contains in an image sensor, contains a photodiode, and we load the charge that is detected by the photodiode into the CCD and then shift that charge down and out the register. So with that, people built CCD cameras. This is Mike Thompson's first camera built at Bell Labs. Steve Sasson at Kodak invented the first self-contained digital camera in 1975. We built spacecraft cameras at JPL. There's an old camcorder And you can't really tell, but they had huge batteries, like the size of a brick on the backside. Weren't very power efficient. This was an industrial CCD camera, maybe in the late 80s. Here's the CCD chip, by the way. So you see the CCD chip actually is not particularly big or anything. But the problem is that all the electronics required to make the CCD work have to be put on these separate boards, and that's what makes these cameras so large. And maybe kind of the end of the evolution is like a Sony camcorder in the early 1990s, which wasn't quite as big. It also impacted astronomy quite a bit, and because of that impact in astronomy, which is a field of physics, the Nobel Prize in 2009 in physics was given to Willard Boyle and George Smith. And the citation said that it was for the invention of an imaging semiconductor circuit, a CCD sensor, which is pretty cool. I got the Nobel Prize. Unfortunately, the Nobel Prize Committee made one small mistake, okay, and that's in the citation, because they didn't actually invent the imaging semiconductor circuit. Actually, that patent goes to Mike Tomset, who was working with them at Bell Labs. But Mike invented the CCD image sensor, and of course he was kind of felt slightly left off when they cited this. But actually, you know, probably it's just a citation problem, but the Boyle and Smith certainly deserve the Nobel Prize. We'll come back to Mike Tomset a little bit later. Anyway, I went to NASA Jet Propulsion Laboratory in the 1990s, and we're building giant spacecraft at JPL. These are for robotic exploration of space, so we send these big spacecraft out to various planets, and they take pictures and do other measurements. This is the Cassini spacecraft here, and you see a person down here in the lower left corner just for a size scale. And this is the camera, this large refrigerator-sized thing on the side of the spacecraft. So these cameras are actually quite large, but they took fantastic images of the outer planets. So the problem is that we wanted to make image sensors and cameras that were a lot smaller. So this was kind of, when I went to JPL, this was one of the demands of the NASA administrator, is smaller, faster, better, cheaper space missions. So that meant everything had to be shrunk down, but in particular for me, it meant that we had to figure out how to make the camera much smaller. So I knew about you know, Weckler's work and other work from the 60s, but unfortunately that technology didn't work very well, and there's a couple reasons for it, which we could talk about later. But I also knew that CCDs worked really well, and I wanted to try to come up with a new technology that would not give up any of the performance advantages of the CCD, but still lead to lower power, more compact systems. Plus, we all know that if you have an electronic system, one of the keys to making it smaller is integration. Well-known fact. So how can we integrate an image sensor into a mainstream CMOS process? And unfortunately, that method that the CCD works, how it works, by shifting charge many times, requires a semiconductor fabrication recipe that's quite different than mainstream CMOS fabrication recipes. So you really can't mix and match like CMOS circuits with the CCD process recipe. It's kind of like trying to make a pie cake. You know, just imagine you want to make a pie and a cake in the same thing and cook them in like one recipe at the same time. It's very hard to do that. So we had to come up with like a different way to build these devices. So I had this idea that we could retain the advantage of the CCD and still use CMOS. And the main idea is that we wanted to get rid of shifting the charge along so many times. I just wanted to shift it once. So we have light come into the pixel, and it generates some electrons. And then we also build the measuring amplifier inside each pixel. That's part of what makes it an active pixel. So we do this in two steps, and you can kind of think of it as like going to the deli counter. If you go to the deli counter, you want to order some goods, the person behind the counter pulls out a container. Now, you don't want them just to start putting your stuff inside the container, because then you're going to pay for the weight of the container plus the weight of the food that you're buying. So you want to put the container on the scale first, zero out the scale, then put your food in it, measure it again, and of course the difference between those two things is the actual product that you're trying to buy, right? So we call that correlated double sampling. We actually do two measurements. So we measure the voltage that's on this capacitor. Oh, you guys are all electrical engineering students, or faculty even, so I can ask you a good question. So let's say I always like to ask this question. Let's say I have a capacitor and a switch and a power supply. And I close the switch, let's say the power supply is 5 volts. I close the switch, let the capacitor charge up, I don't care, 10 minutes or something. Plenty of time, it's like a perfect switch anyway. Then I open the switch. What's the voltage on the capacitor? 5 volts? How many say it's 5 volts? Oh, you guys are just chicken. It should be 5 volts, right? But actually, of course, I asked this question, and the answer is it's not exactly 5 volts. Why? Because when you close that switch, electrons are constantly going back and forth by Brownian motion between the capacitor and the power supply. And on average, it's at 5 volts. But when you open the switch, you never know. There's always a few electrons trapped on one side or the other side of that switch when you open it. And so that always gives you a little extra noise, an uncertainty in the voltage. And we don't know what that is. So we've taken this capacitor and we've charged it up to, say, 5 volts and opened the switch. I didn't show the switch in here. But we don't know exactly what voltage it is because of this, we call it KTC noise, this thermal noise from the Brownian motion. So we measure it. That's the deli scale first operation. So we measure it so we know exactly, and it turns out it's 5.0012 volts. Then we transfer the electrons that we collected from the light generation onto the capacitor, and then we measure it again, and now it's 4.993 volts. And we take the difference between those two, and if we know the capacitance, we know exactly how many electrons were there. Or at least we have a good measure of a voltage that's proportional to the number of electrons. So that's the main idea for how these sensors work. Okay, so once we can do that, and we don't have to transfer the charge so many times, we can build everything else in a standard CMOS process recipe. That means we can integrate on all our analog signal processing, our digital circuits, our A to D converter circuits, all that stuff on the same chip. So now we're ready to go. So we can build this image sensor chip that has all the pixels. Here's a pixel array. And then it's got analog signal processing and digital circuitry and A to D converters and other things on the same chip. Camera on a chip, we called it at that time. Because all those, if you remember the CCD device, it had those circuit boards that were required to make the CCD work. Now we figured out how to shrink them all down onto one chip. And the way that enabled that was that careful design of that pixel. So that allows us to build really tiny camera systems, and that is more or less what's inside your camera phone today. I don't want to oversimplify it. There's actually been like thousands of engineers around the world that have refined that, but that basic idea of the intra-pixel charge transfer to reduce the noise is still used today in every single pixel in every single camera practically on the planet. Okay, I didn't do this work all myself. Almost all engineering is done as part of a team, so this was most of my team at JPL. You know Orly? Yeah. As a couple of these people are now leaders in imaging business. So we invented this technology at NASA for interplanetary spacecraft, but it didn't take very long to figure out that this technology would be good here on Earth as well. So here I am working for a federally funded research lab, NASA. So my job was to go out and try to take this research that we did under taxpayer funding and get US industry to start to make cameras based on this technology. So I went around to a lot of companies and They were all kind of interested, but not ready to commit. Very slow time scale. Maybe, who knows. That was very frustrating. So we finally decided, you know what, we're just going to start our own company and do this ourselves. So we founded Photobit in 1995. Myself, Bob Nixon, Nick Dudamopoulos, and Sabrina Kemeny. So we did a lot of stuff. We, for like years and years, 5 years or so, this was the team in early 2000. We grew to about 135 people, 140 people over the years. Did a lot of really interesting projects. Most of it was self-funded through custom design projects from private industry. We did get a lot of good support from SBIR programs, and then later investment from strategic business partners. Filed over 100 new patent applications in the process of building a company. And then, hooray, in 2001 we were acquired by Micron Technology, which is a big memory chip company up in Idaho. And that's what practically every entrepreneur wants, right? You want to be able to have an exit from your company, because otherwise the value of your company is just a piece of paper. Not even a piece of paper, it's a spreadsheet somewhere in a computer, right? So it's not until you actually sell the company or do an IPO or something where you're liquid that you can exit. So that was let's call it Miller time. Well, it's a dated reference, but beer time anyway. So as I said, so now it's 4 billion cameras are manufactured every year. And by the way, I think that 4 billion cameras a year means about 120 cameras per second. 24 hours a day, 365 days a year. It's kind of mind-blowing if you think about a conveyor belt with cameras going by at 120 per second. It would be a blur. You couldn't even see it. So sales were about 10 billion in 2016. Thousands of engineers are working this around the globe. As I said, I got to give them a lot of credit. Caltech, who runs JPL, has successfully enforced its patents against all the major players in the intervening years. And NASA is now just adopting the technology for use in space. You may think that's pretty funny. I found it kind of irritating. But actually, NASA is an incredibly conservative organization. And when you think about new technology and introducing new technology to markets, you have to think about your customers. So in the case of NASA, we build these spacecraft. They take years and years to get Congress to approve the mission. Then you start doing the detailed design. You build the instruments. It takes years. Finally, you get to launch it, and it's going to someplace far off, like the outer planets, and it takes years and years to get there. So it could be 15 years, 20 years even, before, from the time that you had this idea to do this measurement to the time that the camera actually snaps its picture at its destination. Now, when you turn the power on, it's better work. So are you going to use a brand new technology that's never been tested in space before, or are you going to use something that people have already used and shown to work? Which one would you choose? Right? So it's very hard. It's not really until a technology is compelling for some application that you can displace an incumbent technology. Okay. Now, for cell phones, it turned out that you couldn't use a CCD for cell. The battery would drain out really quickly. You couldn't fit a CCD camera into a swallowable pill camera because you wouldn't want to swallow it, trust me. And a few other applications. That's where we got our toehold in the marketplace. So it's got to be compelling if you want to introduce a new technology into the marketplace. But by the way, here's endoscopy cameras. This was in 2012. Really tiny cameras. You'd much rather have this inserted into your body than that CCD camera we saw before. These are some 16 megapixel camera modules from Sony back in 2012. And just to trace this, by the way, so Photobit was the company we started. We were acquired by Micron. Micron decided to spin it out later as Aptina, and then Aptina was acquired by onsemi, which is where that legacy exists today. There's another company in England, VLSI Vision, was bought by ST Micro, and they're still in business today. OmniVision started actually within a few months of the time we started Photobit. They completely copied our technology, I'll just tell you. And now, today, some of their money is in my pocket. I'm happy to tell you that too. But they're still in business. They're acquired finally by a big Chinese investment company, but still doing business under OmniVision. And then, as with almost everything, when something is successful, the big players come in. So Sony decided to give up its CCD business and go into CMOS image sensors. They are now the dominant player in the business, and Samsung also is another huge player. Okay, I always want to take a moment just to talk about this because as engineers, we ought to think about the impact of our technology on the world, and it's not always a good thing. Okay, there's always new issues that come up with technology. So, you know, selfies and instant communications, which you really need to think about things like Facebook, right? Facebook is really a camera-enabled platform, social platform, just like Instagram, which is owned by Facebook, all right? It's causing, I mean, just every day in the news you hear about Facebook, right? The body cameras, for example, have been very important from a social impact and social justice point of view. Just some amazing things. Security versus privacy is something people have known for a long time. This is when the Boston Marathon bombing. It's amazing that we were able to capture the perpetrators of that crime really quickly. Why? Because they were caught on camera. From everybody shooting pictures of the parade and also security cameras in shops that after a lot of detective work, in a very short amount of time, they were able to find those guys. Drones are becoming a giant issue. I saw a very scary video. It's fake, fortunately, but on slaughter bots. I don't know if any of you have seen that. Has anybody seen that? Slaughter bots. It's very scary, but you should watch it anyway. It's kind of a guess at where this drone technology could go in just a few years, coupled to artificial intelligence. And of course, inappropriate use, also an amazing thing that I never, ever, ever expected that people would be taking the kinds of pictures that they take and posting them. So you just never know. And there's probably 20 other examples I could put up here we could talk about. And you know, what do you do? I mean, it's, you can't anticipate all the negative ways that your technology is going to be used, but it's worthwhile thinking about it for a little bit. Is there anything really bad that can come out of a technology as engineers? There's no particular solution. It seems like entropy prevails and people will always find some negative use for a technology that you introduce. But ultimately, as engineers, we have to take some responsibility for our creations. Okay, so this is the happy day that just happened. So we get this Queen Elizabeth Prize. Here's Mike Thompson again. Yay, Mike. He didn't get the Nobel Prize, but he got this other big prize with us. And Nobu Teranishi, who invented the pin photodiode, and me. And George Smith, who was one of the CCD Nobelists, received this prize. And I got to meet Prince Charles, and you can see I'm smiling. But what you don't know is I have no idea what he's talking to me about. He tends to speak in that strange English accent, and I couldn't understand what he was saying. It was very frustrating, but I tried to smile and thank him. Anyway.
Did you take a picture?
What's that?
Did you take a picture?
No, you're not allowed to bring any cameras into Buckingham Palace, unfortunately. It all has to be taken by the official palace photographer. So I did have a funny thing happen to me, though, that, oh, what the hell, I'll tell you. You know the actor Will Wheaton? He was in Star Trek, and then he was in the, whatever that other show is. I forget the name right now. The one that takes place like Caltech or something. Big Bang. So Will Wheaton is this a famous, kind of famous actor. And I was at some meeting, and he was there giving a talk, and I was giving a talk, and like we're getting a chance to meet him with some other people, and his handler's like, whatever you do, don't get too close to Will. He gets very nervous around people. You know, if he reaches out to shake your hand, you can shake his hand, but otherwise, you know, stay in your place. And whatever you do, no pictures allowed whatsoever. We'll have an official photographer here to take your picture. So meet Will and talk and tell him what you know, the technology we developed at JPL, which happens to be just a few miles from where he grew up. And he's like, no way. He goes, can I take a selfie with you? And his handler just like completely flipped out, but couldn't say anything because Will's in charge. So strange things happen. Okay, so I want to get to the Quanta Image Sensor, which is what I'm working on today. This is the new music part of the talk. So a very small group at Dartmouth. Some of these guys have graduated, and women have graduated, and there's some new students that didn't get their picture here. And if he looks funny, that's JJ Ma. It's because he's photoshopped into this picture. So the idea with the Quanta Image Sensor is that I've been asked to write a book about what the future of digital still cameras might be. And I thought, okay, you know what? We're making pixels that are smaller and smaller. You can't store very much charge in there. Where are we going? So I thought, hey, why don't we think about a image sensor chip that takes advantage of the shrinking pixel size, and we'll make a very tiny specialized pixel, which I call the JOT, which is Greek for like smallest thing, which could just be good for sensing a single photoelectron. And then we read these JOTs out. We have like lots of them. Read them out at a high frame rate so that the JOT isn't filled up with an electron already. And then we collect all this data in X and Y. These are all the JOT data for a single frame. And we collect many, many frames of them. And then we create the actual pixels by combining JOTs over some spatial neighborhood and some temporal neighborhood as well. Call this a cubicle. So it has some X and Y dimensions, 4 by 4 in this case, and then also some time dimension, maybe 4 frames. And then we use that data in the cubicle to create a single pixel, which is why JOT is the smallest thing and the pixels are next. And I was thinking, okay, so maybe we go to like 1 billion JOTs and we'll read them out at 1,000 frames per second, which if you just multiply that, that's a terabit per second, by the way, and also consume less than a watt. So that was kind of the vision I was thinking about. It's a new way to think about photography or capturing images. It's just one photon at a time, but we count them very rapidly. And then later, once we have all that digital binary data, the rest is up to computer science, basically, right? There are just so many ways you can create the pixels once you have the raw data. So that was kind of the vision. I had no idea how we could actually make that in 2005. In fact, when I had this invention in 2004, I was actually running a MEMS company as a CEO. I had no time to work on anything. So it wasn't until I got to Dartmouth that I had a chance to explore this. This just explains that concept again. We collect this binary data and then many frames, and we use that to create individual pixels. Okay, so here's another factoid that you need to know, is that if you think about light coming from a light source, which is emitting photons, and photons are quantized units of energy. It's kind of quantum mechanics, so to speak, in action. The problem is that a light source does not produce photons at a very steady rate. It's not like the steady drip, 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 drip of a faucet, water faucet, okay? It's more like traffic on the highway. So sometimes it's bunched up and sometimes it's not bunched up. So it's irregularly spaced. And if you count over some period of time, sometimes it's like counting traffic or cars on a highway. Sometimes you only count a few cars, but if you happen to count over this period, you would count more. So if you did this measurement over and over again with a short time window, you would have a pretty high variance from measurement to measurement. Okay, this is the so-called photon shot noise. Okay, So even though it might be a perfect source, in many ways, you still have this Poisson arrival rate issue leading to shot noise. So if you try to take a picture under dim light with your cell phone camera today, you'll notice that the dark areas have a lot of noise, pixel noise in it. Doesn't look very good. This is almost always due to photon shot noise in the low light condition. So it affects our ability to take photographs. So if we look at this arrival rate, for example, we'll talk about a quanta exposure H, the photon flux and some integration time, and just simple example of H equals 1, it means that on average there's 1 photon arrival per measurement cycle. And then here's the ugly equation for the probability of K arrivals, where K is like 0 photons, 1 photon, 2, 3, 4, and you plug that into this equation. If you know what the average is, you can get the probability for each of the arrivals. So here's a little Monte Carlo simulation over 64 measurements, and sometimes we get like 3 arrivals or 1 arrival, 0 arrival. Don't forget the average is supposed to be 1, but you can never really tell from measurement to measurement what you're going to get because of this shot noise. For this quanta image sensor, we only care about two states of interest. One is that there was no photon, which we'll call 0. Okay, and if we plug that into this equation, we just get e to the minus h. And the other is that we have at least 1 photon, and that's 1 minus e to the minus h. And if we plot that out, we see that the probability of having 1s kind of comes up rapidly, and then slowly asymptotically approaches unity. That's different than a normal image sensor, which once you do full exposure, it's very linear and then is completely saturated. So it's a different imaging characteristic, unless you're down here in the low flux range, in which case it's more linear. Okay, so if we take that same curve that I just showed, this curve, the blue curve, and I replot it on a log axis on the horizontal bar, then I get this blue curve. And so this curvy part is the linear part, and then this is that overexposure part that's kind of approaching saturation. Why do we care about this curve, this S-shaped curve? Well, the interesting thing is that in 1890, and I bet this is one of the few talks you've gone to where we can reference papers from 1890, and they're still relevant, the density of old-fashioned film has exactly the same exposure curve. Now, what does that mean? It means 2 things. One, the reason why this overexposure part here climbs is because if you think about photons hitting an array of pixels, or think of it as rain hitting tiles on your back patio, okay? At the beginning, you know, there's raindrop on a couple tiles. Eventually, some tiles get 2 raindrops or 3 raindrops, and there's some tiles that it takes a long time before that tile is finally hit by a drop of rain. So that's that behavior up here. It takes a while to saturate where all the tiles on your patio have been hit, or all the jots have been hit by a photon. In film has got this is old-fashioned film, which I have to say many of you may not know anything about. But old-fashioned film used to have silver halide crystals inside the emulsion. If a silver halide crystal is hit by a photon, when you develop the film, there is a chain reaction that causes that silver atom to wash away. If it doesn't get hit by a photon, no chain reaction, and that silver atom stays there in the emulsion. So it's kind of binary, right? Either the silver atom washes away or it doesn't wash away, just like our jot, 0 or 1. And the probability of a photon hitting a silver halide crystal is also the same thing. It can, eventually, all the silver halide crystals will be hit by a photon, but not at the beginning. So the characteristics is exactly the same. And if you talk to photographers, they love this characteristic about film because it gives them this extra overexposure latitude. If you look at a movie that's shot digitally without any additional processing and compare it to a film movie, you can see right away the difference in the way the image looks. Your eye can pick it up right away. And it has a lot to do with that D log H curve that I'm showing you. Now, what people do is they try to take the digital signals and process them so they can kind of come back to this D log H curve. So it looks like film again to your eyeball, which is much more attractive. Okay, I'm just showing this for reference. This is the same thing now as a log plot. And now you can see there's this big linear region here in the low exposure and then saturation. Okay, so let's take an ideal Jot pixel, and if we read out the voltage from this pixel, and the voltage is proportional to the number of electrons, so here's voltage, and here's what the probability of what the readout voltage is. And let's say that I'm shining light on it that has an average of 2 photons. Then I would expect that some of the times, look at the purple arrows here, the delta functions. If it's a perfect sensor, then I should read out either 0 electrons or voltage corresponding to 1 electron or 2 or 3 or 4. And the amplitudes of these delta functions is defined by the Poisson probability mass function, which happens to be this for h equals 2. Unfortunately, we can't do a perfect readout of a pixel. There's always some electrical noise that's added to the readout. So if I add some noise, then the perfect peak is broadened by the extra noise that's added in during the readout. So the probability distribution gets wider, and as I add more noise, these peaks get more and more broad due to the added noise. And finally, if I add enough noise, like if it's equivalent to 1 electron RMS of noise, I can't see any peaks at all. I just get this smooth distribution out. The noise in your cell phone camera is probably like 2 electrons RMS. So you'll never see these individual electrons coming out in your cell phone camera, at least not today. But if we can get the read noise down to maybe 0.15 electrons RMS, we can really tell a difference between, in a very likely way, between 0 electrons or 1 electrons or more being in our pixel. And that's where we want to go with a photon-counting image sensor, is be able to detect that reliably. And all we do is build a little threshold circuit that says, hey, if the voltage out of the pixel is less than this valley, then there was no photons received. And if it's greater than this valley, there was at least 1 photon received. And as long as this valley touches down to 0, more or less, we have pretty reliable measurement. We could characterize that by a bit error rate, and it just shows, this curve just shows that when you calculate that, when the read noise goes from like 0.3 electrons RMS, the chance of having an error in your count is 1 out of 20. If you can get the read noise down to 0.15, it's 1 out of 2,500. This is a very steep curve. So we really want to get read noise down to here. And like I said, for your current technology, it's typically up over here by the clock somewhere at 1 or 2 electrons RMS. Okay, so we're getting more technical. So counting photons digitally is not a new idea. There is this single photon avalanche detector that exists. So we could use this to build a quanta image sensor. And people are now starting to use this to build a quanta image sensor. So you have these single photon avalanche detectors, and you build an array of them. This is a 512 by 128 array, for example. And the idea is that if you get just 1 photon in here, this is a bias to avalanche range, and 1 photon will generate 1 electron, and 1 electron will start a chain reaction of avalanche, and you'll wind up with a lot of charge. And it kind of self-quenches after that. And then you can tell, you get a lot of charge out of 1 photon, and you can easily tell whether that SPAD pixel was hit by a photon or not. Okay. So I don't like SPADs. I mean, nothing personal about SPADs, but here's some reasons. So the photon number is very difficult. So it can tell between 0 and 1, but you can't get a photon number out because you get Fano noise in the avalanche process. Also, the impact ionization requires large electric fields over many free path lengths, and that results in a high voltage, which we don't really want in an advanced CMOS fabrication process. Also, because you have to have good isolation between these avalanche diodes, you need a large interpixel spacing, and that gives a low pixel density in the output. Wow, I need to go faster. Okay, manufacturing is a problem, reliability is a problem. So our approach is just to use this low capacitance sense node where the change in voltage is just the charge divided by the capacitance. If we can make the capacitance really small, like 0.16 femtofarads, then we can get 1 millivolt out for a single electron. So we invented a new kind of device, which I'm happy to talk about later in Q&A, but basically we tried to figure out how to build a really low capacitance sense node, kind of like an island that's isolated from everything, and then the trick is how do you get the electron to that island, and that's what this device allows us to do. So here's a typical curve I just showed you before that's theoretical. Here's the kind of data that we get out. This is for an average of one electron arrival. We get distribution that looks almost perfect relative to the Poisson, what we expect from the Poisson mass distribution function. And if we double the light intensity, it behaves exactly the way it's supposed to behave as we turn up the light. So this just shows that if we can get this really low capacitance, which is experimental data, I should say, at room temperature, by the way, even without avalanche, we can do single photon counting quite nicely. It agrees pretty well with theory and, yeah, low read noise. So we're down to about 0.17 electrons RMS. If we don't do that thresholding circuit, we can get photon number out very nicely, which is important for a lot of fields. If you just want to know how many photons came in, we can count that pretty accurately. It should be kind of intuitive that, hey, you know what, if we count one photon, we could also count multiple photons doing a more complicated kind of A to D converter. This would be like a 2-bit multi-bit pixel. I can talk more about that later as well. Another important thing is that we want to make sure that in the dark we don't get a lot of spurious counts. So this particular device structure gives us about 0.16 electrons per second on average at room temperature, which is a very low number. And even if we look at the dark signal here, if you're familiar with these things, we even can still see quantization bump in the dark signal. This device was built in a stack structure at TSMC. I can't show you a picture of that, but this is where the state of the art is now for image sensors. We have a detector layer and we have a circuit readout layer. These are micro lenses on where the light comes in, color filters, pixels isolated by trench isolation to reduce crosstalk, and then there's the readout that we talked about. The Deli scale is here. You can't really see what's going on, but then there's this hybrid bonding between wafers, very high density, and then a circuit layer for additional logic. So we built an image sensor using this kind of process at TSMC, went to a cluster parallel architecture, built this chip. So this is 20 different 1 megajot arrays. Each design is slightly different. I won't talk about the circuit, but it turns out it works, which is actually kind of amazing credit to my 2 graduate students who did this project. One worked on the detector layer, the other did the circuit layer. So we built a camera, we took a picture of a picture of a leopard, and then this is what we get out for data. And then actually, we used a denoising scheme that comes out of Purdue to produce a pretty nice looking image in the end. There's a little fixed pattern here, which is still need to work on a little bit. But anyway, this is a 1 megapixel photon counting image sensor that's operating at 1,000 frames per second, which is useful to many of you perhaps. And the total power dissipation for the array, including pads, is about 17 or 18 milliwatts, which is a very low number. So anyway, lots of applications for this in, as I mentioned, photography, cinematography, certainly scientific sensors for low light, defense applications. One thing that I learned with the CMOS image sensor technology is that basically the killer applications find you. You may think you're smart and you know what your technology is going to be used for, but it's often somebody outside your immediate circle that comes up with another application. So it's kind of an interesting phenomenon. And last but not least, we decided, Soleil and JJ, my two PhD students, to why not start a company? So GigaJot is now out in California, and just at the very beginning, two-person company right now to start to look at commercial possibilities for this technology. So I think I will end right here. Thank you very much.
Thank you, Eric, for the wonderful talk. Any questions from the audience? And whoever has a second question, please raise your hand so we can bring the microphone to you.
Thank you very much for a very interesting talk. My question is very non-technical. Is it public, the exit amount for the photobit company?
Say that again. Is it public?
How much the company exited for?
The old company that we sold?
Yeah.
Yeah, no. Not public information.
Okay.
More than $1.
2?
Less than Google.
Hello. Yeah. So you mentioned that the capacitance is made very small in order to detect the small change in the charge. But wouldn't that also ramp up the noise, the thermal noise? And how is that effect overcome?
The thermal noise, you're talking about what we're talking about with that capacitor being charged up?
Yeah, the KT noise.
Yeah, so we still use a correlated double sampling to basically zero out the Delhi scale, the floating diffusion node, measure the voltage on it after we reset it, transfer the electron to that node, measure the voltage again. And that's where our voltage signal comes from.
I have a quick question. Kind of looking back in the era when you were working in photobit, all right? And you worked for 5-6 years in this company before you sold it. Looking back now, would you have done anything different with your exit strategy or anything else?
Well, I'll just say that we didn't know anything about running a business. I had a paper route when I was growing up. That was the extent of my business knowledge going into this company. You learn a lot actually with a paper route, but yeah, there are many things we would have done differently. But I'm quite happy with the outcome. So I don't have any regrets or anything about what we did. I think we did a good job. We got the technology out there, which was my main goal, to get people to use it. Kind of overachieved in that area, and you know, what else could you ask for in life? So yeah, maybe I could have made more money in the end. I don't know, but I'm not complaining.
Yeah, I have a question regarding the Quanta Image Sensor. Do you have to do anything special, maybe differently than you do with a CMOS sensor, for capturing color?
Right, so was that 2 questions or 1 question?
Just a single question.
Yeah, so color is very interesting because our target for the JOT size is sub-diffraction limit or some very small number, maybe down to 200 nanometers. So it's like, well, how does a color filter array work at that size? How does the photon couple into this thing? Actually, I'm pretty confident that the photon will couple in, but CFA material is notoriously difficult to process. So kind of the backup scheme right now is to cover a few jots in a local net, like 2 by 2 or something with the same color filter. We've actually built these, but somehow my students left before we got a chance to test them. So next generation will test them. I think it should be okay. Then you have to treat each color as a separate bit plane, basically. Or, I don't know, computer science guys will probably do something different than that. I think there's a lot of clever things to do. Yes?
I have an interesting question. I'm doing a lot of high-speed detection for that. So obviously you have very low speed. And for
By the way, from an image sensor point of view, people think of this as pretty high speed, by the way.
From a data rate, I think it's slow. So for signal to noise ratio.
Hold on a second, just back up. Remember, the output of, if we can do 1 billion jots, which I think is quite possible, is a terabit per second. That is not a slow data rate. It's like almost an impossibly high data rate for getting data off a chip.
Well,
but I understand I know where you're going in this, but I just
I guess you're doing a lot of parallel processing.
That's right.
For a single channel, and you need a very high signal to noise ratio, and so your bit error rate have to go down to 10 to the minus 12, right? So what is your solution, you think, I mean, in our area? I mean, that's a very
fortunately, I
difficult
think
problem.
I think there's a lot of applications where bit error rate of 10 to the minus 3 is just fine.
Yeah.
Especially in imaging, you won't know the difference because you have shot noise in the background anyway. For optical communications, yeah, I think this is not designed to be a good device because that correlated double sampling that helps us beat back the noise takes time.
Right. So the industry solution is you build error correction chips, and which consume a lot of power to correct that.
Right.
So that's the current solution. I always try to figure out any other better solution for low power.
Yeah, so if you know the data that's coming in, then of course you can do this kind of error correction. But if you have no clue what's in the image that you're looking at with the camera, it's hard to tell whether that photon you just received is you detected wrong, either as a false positive or otherwise.
So you contrast the CCD to CMOS, right? And that's direction you get low power, small form factor. I think you mentioned, but can you really elaborate on from CMOS to the Quanta imaging sensor? What is the fundamental key new measurement or advantage that we would potentially see?
Right, so probably for consumers, it's not clear what the advantage is. But for a lot of low light scientific imaging applications, being able to have such low read noise is very important. Also, for, oddly enough, quantum information science, which is also quiz. So you need the quiz for quiz, as it turns out, because the photon number is very important to know. So you can collect photon number pretty accurately with this device. It turns out also that this device I put on the list there is a random number generator. It turns out that if you collect data, illuminate this device, you get a vast amount of random data, which is very random. And so people are interested in using this as a random number generator, as it surprised me. I don't think it's a killer app that I didn't expect, but it was an application I didn't expect, for sure.
And my second follow-up question is, have you thought about the connection of the QES with the super resolution imaging technique in medical imaging, right? When you're familiar with these STOMs and PALMs, where they use random activations and you capturing, right? So do you think it would be a good marriage of this quantum imaging with that super resolution methods?
Actually, I don't know enough to be able to answer that question definitively. A number of people have suggested that it was a good possibility that it could be useful there, but I haven't investigated it, and I don't know enough to be able to answer that off the top of my head.
All right, let's everybody thank Professor Fossum one more time.